Well, the voltages basically look okay. Near enough. Let's try this again with the camera. So we'll switch it on. And what do we have? Well, that's the big transistor. And it's about 60 or so. Next to it is the LM317 and 337. They're cool. This is the other hot one. And then we have that one next to it, which is hot, 80 degrees. And then the last one is cold. So there's another hot one there. Let's have a look at that one. Well, I'm not sure what it is, but it's marked in and out. So we can have a look to see what voltage is coming out of this and then going into it. Okay. So in is about 17, out is 5, so that's a 5-volt regulator, so that's dropping quite a bit of voltage actually, so you'd expect that to get pretty warm. So I'd say this lot just runs hot. I mean, it's bolted to this heatsink and this should be bolted down. It's not at the moment, which is connected to the chassis, so this obviously is designed to dissipate some heat. I'm a bit surprised they run as hot as they do, but they drop in a fair bit of voltage. These diodes now don't seem so hot. They seemed hot before, but not really now. Obviously, it's doing a bit of work here, but I don't think that's a fault. You know, I don't have another one to compare with, but I don't think so. So the next thought is that we have like a phantom fault here. So it's stuck in protect because there's a problem with the protect circuit itself, whatever is monitoring the amplifier. So it thinks there's a fault. So we need to have a look to see where that is. Well, this is the protect circuit. We can see that because we have LED protect, we have relay drive here. So this is monitoring various conditions. We have mute drive as well, so it mutes the audio. Time in. Then this seems to come to, well, a number of places actually. 1 through to 7, so it was 7 places. There's signal time in. And it's telling us it should be -10 on the base of Q2. Yeah, it gives us some voltages here. So I'm assuming that these voltages are in normal condition, not in the protect condition. This is all ground. So I think if we find these components and we can measure some voltages, maybe that will give us some idea of what's actually going on. There's also some more circuitry here which says relay drive, on or off. This looks like it's monitoring temperatures. You see NTC heatsink. Okay. This does drive the LED protect, where it looks like that one doesn't. So I think this is a thermal shutdown. Looks that way. So I'm still going to concentrate on these. So I'm going to try to identify the transistors. Well, we are in this area, Q2, 3, 5, 6 and so on, okay, which is here. We can see all that way up to Q7, Q21. So seeing as I've actually found this part of the circuit and it's marked collector, emitter and everything quite nicely, let's just see if we can spot anything obvious here, okay? And then if not, we'll measure some voltages. So is that a bit short? I'm just shorting against the nearby resistor. No, I was just shorting against something. Okay, so it looks like this is an NPN. Let's get onto the base. I don't read anything. Maybe I have a bad connection on it. pushed over a little bit. So Q2, base, reads open, meter's working. That's a funny reading. Go the other way. Reads like a diode. Reads like a diode. So if that one is a PNP, that actually reads good. Okay. That is Q2. What's this little one up here, by the way? Is this part of the circuit? Q4, okay. Yeah, we can see that as a PNP. Well, that reads open. What's this one? This is Q4. Sorry about the noise, guys. Cafe next door closing. Oh, typical. See, that's an NPN. Q4 and Q7 are NPN, okay. Reads okay. Positive to the collector. Yeah, this reads open like you'd expect. This was Q2, so negative to the collector. Reads open like you would expect. Q3, this is one of these PNP ones. Reads like a junction. Reads like a junction, okay. Q5, look at this one. Reads like a junction. Same. Q6. So these all read okay so far. Here's Q7. I think this was one of the NPN ones. Let's have a look. Yeah. Oh. That doesn't read right. The emitter, let's just do the other way around. Check on the schematic, so Q7 is here, NPN, so red on the base, junction to the emitter. Right, so that's a bad transistor, Q7. That could easily be the cause of the fault. While we're here, let's just check these diodes. Reads okay. Reads okay. Reads okay. Any more transistors after 7? Let's see. So up to Q7 we've tested. Q2, 3, 4, 5, 6, 7. Q21 we should probably check as well. Q21 is here. Okay. This is another NPN. Let's have a look. So maybe it was another PNP, my mistake. Let's see. No, this doesn't read. Have I got a good connection to the base? Let's go. Yes, we can see it. Nothing. Well, a funny reading. Let's go on this one. That reads okay. And to the collector. Reads okay. So, NPN, which it is. So, Q7 is faulty, and we can see exactly where this is in the circuit. So, I would expect that probably could give us a error, protection error. Yeah. Triple check it. Reads okay. Does not read okay. Right. What is this thing? BC618. Okay, I don't have this transistor BC618, but I can see where it is in the circuit. So we know there's a fairly low voltage, 23 volts here. It's mentioned 11 volts here, so they must all be low. That's like a voltage divider between those two. So halfway in between, roughly, on the base. And this is coming out, says 10 volts minus. So there can't be much voltage around here. So let's see if we can find a data sheet for this and then see if we can find an equivalent that I do have. Because I don't think this is very critical. Oh, well, that's just sod's law because it's a Darlington. Maybe is that why it doesn't read to the emitter? I'll probably have to take this out of circuit and test it because this could actually be okay. The thing with this Darlington transistor, internally, it's like this. So we have base collector emitter, but we have two base emitter junctions in series here. The idea of this, of course, is so that it multiplies the gain. Whatever the gain of this transistor is multiplied by the gain of this transistor. So if this was 20 and this was 20, then the gain would be 400, okay? So that's what it is. Darlington, okay? Now you'd think you couldn't measure these with a multimeter because you would see the base collector junction, but you wouldn't see the base emitter junction. But generally that isn't actually the case. So these are some TIP122 transistors. This is a Darlington transistor. This is the datasheet, NPN epitaxial Darlington transistor. So we can have a look. And in actual fact, it's basically how I showed you. There's a reverse bias diode here, a couple of resistors, but that is basically what I showed you, okay? There it is, TIP122. And if we look at this with a multimeter in diode mode, NPN, so positive to the base collector, we read a diode junction, yeah? And base emitter, we also read a diode junction, but it's a higher reading. Now, that's kind of what's happening with the one in the circuit, but it's much higher and doesn't show it as a diode junction. If we look at this on my component analyzer, it knows it's a Darlington transistor, okay? It's saying there's diode protection between C and E, which there may not always be. Resistor shunt between B and E. And the gain is not accurate due to the resistors. And it's saying the gain is 22, but it could well be quite a lot more than that. Okay, could be more than that. So that's what it's telling me, and it's showing me the base emitter junction as 1.34, which is kind of like two diode junctions together, okay? So I'm going to have to unsolder the other one to prove definitely if it is faulty or not. And there's a very good chance that it isn't faulty. Here's the Darlington transistor. So we'll go from one end, red in the middle, which is the base. And that reads this funny reading, which is like two diode junctions. In actual fact, you can see about 1.2. The other way, 0.68. So that 1.2 wasn't something in circuit, it was a device. And from what we now know about Darlington transistors, that kind of makes sense. So let's see. Right. Yes, you see it is okay. Look at that gain, 20,592. I would assume that this one doesn't have the internal resistors. That's why we're actually seeing the gain. That's massive, yeah. This is what Darlington transistors do. And the base emitter voltage 1.5. Because it's a little bit higher than the other one is probably why the multimeter is giving a different reading on that. Okay. So, red herring, Darlington transistor, we'll put this back in. The next option then is to measure some voltages around this circuit. We have the schematic, so we know what voltages we should have, although I don't think it specifically says if that is operating or in protect mode, but I'm guessing it's operating, so let's try. we need to take some measurements. I'm just going to check something first. I'm still a bit suspicious about these capacitors. I mean, I think they're okay. I need a battery for my capacitance meter, but I use the multimeter just to check in circuit, and they were like over the limit of that one. Yeah, I mean, these are 12,000 microfarad each, so I think they're in pairs as well on the low voltage plus, high voltage plus and minus, whichever way around they are. So what I've done is I've just attached scope probe. Here you can see my scope probe. So this is set to 10 times. This is set to 10 times on here. I'm on AC coupling. I just want to look at the ripple on here out of interest when this thing isn't actually powered up as such. Well, it's powered up, but there's no load. It's not driving any music. Yeah. Let's see what that actually looks like. So you can see the scope there, and then let's see what we actually have. I'll just attach the mixer board as well in case I don't get a good reading without it. I have the scope set to times 10. It's a times 10 probe. It's set to 1 volt per division. I'm on AC coupling because I want to look at the ripple, and obviously the high voltage on here will go up. At the moment, I think the collectors of the transistors plus and minus are getting about 45. I'm a bit suspicious about these capacitors because they should have like a plus and minus 52 and 104, and it's about 45 and 90. I mean, maybe the tolerance isn't that close, and my mains voltage maybe is 220 rather than 240. So there are some factors in here, but I'm interested to see what that looks like. So let's switch this on and let's have a look. I'd expect the trace to go off the top of the scale first, yeah, like so, and then it'll come back down and we'll be able to look at the ripple. So that's ripple. Can you see it there? And it's about, let's see, well, it's not a lot. I mean, it's less than a volt, maybe a third. Let me just turn the sensitivity up a little bit. That's on 500 millivolts. It's about 230, 150 millivolts, something like that. So there isn't a great deal of ripple on that, considering as a percentage of the voltage rail. Let's look at one of the negative supplies as well. So we'll just move the scope probe. So I'm on the collector of one of the negative side transistors. What do I get? Off the bottom. Wait for it to come back up. Okay. And that's about the same. Yeah, there isn't any real great difference there. 140 millivolts when it triggers on it. So there's not a lot of ripple on those. So I'd say these capacitors are actually okay. To be honest, they just look a bit old, but yeah, that's what we seem to have. I'm just going to check on these devices that are getting hot on this heatsink as well. This is this plus and minus 15. It reads about plus and minus 16 at the moment. I want to see what we have there. That's one of the large transistors. The voltage regulators, the 317 and 337, are not getting hot. These are. Okay, so what do we have on this? Let's have a look. Well, off the top of the scale, wait for it to settle down. Oh, that is well over a volt of ripple. Yeah, look at that, 1.6 volts of ripple on the plus 15. Look at the minus. Okay. Am I going to see the same here? Let's check. On. Yeah. About the same, 1.2 volts. So that kind of ties in with the fact the transistors are running very hot, the diodes were running hot. We have a lot of ripple, which tells me that something is drawing more power than it should off the plus or minus 15. And I think that is probably related to the protection fault. I don't honestly see it should be that much, you know. I mean, it could just be bad capacitors here, but well, we can test them. But to me that seems really excessive. Let's have a look at the output from the 5 volt as well. This one I can actually get onto the diode which is connected to the out pin. Sorry, it's under the oscilloscope, but I'm sure you know where I am. So this is the 5 volts. What's this giving me? That's smooth. Okay. So there's some problem here. Something on the plus and minus 15. That I'm pretty sure it goes up into the mixer. There's a couple of cables here, so let me have a look to see which cable it is. I can check on the schematic, I think, and then let's disconnect the mixer panel. See if something on there is drawing too much power. Okay, so there's 2 connections that go to the mixer board. CN1, which is this one, 6 pins. And we can see this has some signals on it. Plus 6 dBu, plus 6 dBu or something. Look like audio signals going to these op amps. Ground, I would say, lamp. Okay, and then the other one, ignore these are like test connectors. Yeah, which I can see on the board. The other one is this one, so we can see we have 3 wires there for plus 15V-M. I'm pretty sure this -M, this must be mixer. So plus 15 for mixer, minus 15 for mixer. These are all ground. 5 volts up to the mixer, and then limit lead and protect lead, and this plus pH. Okay, so that's powering the mixer. So I'm going to disconnect this connector and have a look again at the ripple on those large transistors. Or for that matter, just point the thermal camera at them, I think. But we'll see. Well, I have the scope probe here. So that's the positive 15 volts. This we're now going to disconnect. I mean, obviously, the mixer panel will be taking a fair bit of load anyway, but let's see what happens now. We'll power this up. Let's get the scope back on the screen. And we still have quite a bit of ripple on there, actually. 0.5 volt. Okay. This is the negative rail. About 0.5 volt. I wonder what the thermal camera shows us. That's one of the transistors, 33 now. These are the diodes that we're getting very hot in the middle. Just get the glare off the screen for you. About the same temperature now. And then this is the one on the 5 volts. No, actually the large one actually. The 5 volts one is a bit further along. So they're much cooler. But you would expect that because the mixer's not attached, so it's not powering the mixer, yeah? This is a bit of a strange one. I'll take a few voltage measurements around the protect circuit, but at the moment I can't really get my feet on solid ground here. So I know we have a protect area. I know that the voltages on the amplifier itself are okay. There's no ripple really. The output voltage is 0 on the emitters. So they're balanced. They're not having a DC offset or anything like that. So that is basically okay. I've got this issue down here, which if you ask me, that is too much, but I'm not quite sure exactly where the problem is. If it is that, there's obviously some current being drawn because it was a 15 plus and minus and a 15 plus and minus M, so for the mixer, and this itself will have some circuitry down here on plus and minus 15. And I can't find any faults anywhere, and I can't find any faults around these transistors in the protect circuit. So let's have a look at the voltages here. And I think we have to sit and think about this and figure out how maybe we can diagnose it. We can see the various voltages marked here. I'm a bit uncertain on this one, minus 23, if that's pointing to the collector of Q3. I'm guessing that one points there. All the rest I'm fairly certain are quite obvious where they are. So I've made a note of all these to save me keep referring back to this screen. Let's have a look to see what we have. So Q2 base appears to be the input to this circuit. Okay, this one. See if I can get over to that easily. Push it forwards a little bit. Yeah, so that's there, Q2 base. This should be minus 10 volts, so this is a good place to start. Well, we have minus 3. Okay, so that is wrong, and that's probably what's switching this. If we look at the schematic, we can see there's an input here. So if this is minus 10, and look, there's minus 9.3 on the emitters, which we can test, by the way. So with a PNP transistor, the base has to be lower than the emitter, look, by 0.7, and that turns this on effectively, okay? And that will affect everything else in this circuit. That no doubt is why the protect LED is on, okay? So I think we can say straight away the input here is incorrect, which we know because we have a protect light. So let's have a look at this. If we know there's about 3 volts on here, if this is lower, then the transistor is switched off, and minus 9.3 is definitely lower than about minus 3. Let's see. So emitter Q2 is there. What do we have? Minus 10. So we can see straight away this circuit is triggered. That's why we have the protect light, which we know we have. So we're going to have to figure out now to see where that signal comes from. And it looks like it comes from a lot of places. Number 1, 2, 3, 4, 5, 6, 7. Now, unfortunately, this schematic is like an image. It's not searchable, so I can't just search for that. I'm going to have to figure out what these mean. I'm expecting to some extent those numbers 1 through to 7, perhaps the pages that goes to. So I need to find this signal time in. And, well, mute drive I'm not too worried about. Well, I think what we can say is that signal doesn't come from the mixer, because the only connections to the mixer are CN1 and CN2. And this is CN2, and we can see this is all power apart from plus pH. Oh, that's phantom voltage. That's the 48 volts. I've seen where that actually comes from. It's over here somewhere. 5 volts, 12 volts, 48 volts, phantom, okay? So that connector is only power. Plus or minus 15, phantom, 5 volts, and then the limit LED and the LED protect. So that's just the LEDs being driven from here, okay? So time is not coming from there, obviously, and then the other connector we see is here, CN1. We have lamp minus 12, but these other pins don't have a signal name on, and if it was the same signal, it would say, I'm certain of that, yeah, time in. So that must come from the amplifier PCB, and that's this schematic basically. We have this circuit here with this TL034, but this is limit, yeah, limit LED. This is limit on, limit off, so this is nothing to do with the protect. This is mute. So where is the protect signal coming from? What's this monitoring? It must be something connected to here. Well, it appears to come from numerous places. So look, time in 6. Okay, this is monitoring a positive temperature coefficient. This is built into the transformer. Oh, this will be this funny little wire here coming out of the transformer. What's that read? Why are these open? Unless I'm not getting a good connection on it. I wasn't getting a good connection on it. So it reads 784 ohms, no, 78.4. And I assume when we warm the transformer up, that goes up. We can try. Well, it doesn't seem to change. It's actually going down a little bit. I mean, the transformer's a bit warm now, yeah, it's not hot, but okay, so that's that one. So, yeah, this has a positive supply on the emitter. Okay, it's a PMP, so the base has to be lower than the emitter to turn on. The same positive supply goes through this PTC to the base, and that forms a voltage divider with R13. So, the higher the resistance here, the lower the voltage here. Yeah, you can see that. If this one is a lower resistance, then the voltage here is higher. Okay, and if this is a higher resistance, because it's forming a voltage divider here, the voltage goes down. So at some point this will get hot. It'll reach such a resistance that this switches on because the base is less than the emitter, and that puts a positive voltage on here, and this timing voltage will go up. Now we can figure out if that circuit's being triggered by measuring across D2. Yeah, if D2 is conducting, positive here, so in other words it's more than the -3, we know there's a problem with this circuit. So let's have a look. So we need to find Q1, which is here, and there's D2. That's what we're really interested in. So Q1 collector should be positive. It's actually minus. Emitter is 24 volts. We'll come back to that in a minute. D2 minus 4.8 minus 3. So that is not conducting. This end is more minus than the cathode. Okay, so it isn't conducting. Maybe I misunderstood the voltages around Q1. Let's have a look. Yeah, I had it upside down. So is the 24 volt supply in here? That's actually correct, 24. Yeah, so we had more negative here than we had here. So this is not conducting. Yeah, so that isn't causing the problem. Now we need to find all the other instances of this timing. I've not particularly come across this thing before, but what it's basically doing is pointing in the direction of each signal. So 7 is pretty much straight up, which is there, yeah, timing 7. So that is being triggered basically by the NTC on the heatsink. So this is the negative temperature coefficient resistors on the heat sinks. Okay, if either of them overheat, it triggers that signal. Timing 1 is kind of over that way, and this one is here. Now this one appears to be checking that we have power here. See the two fuses? I would say that this is making sure that the fuses are okay. Then we have timing 6 and 4, which are up here somewhere, and also 2 and 3. So there is 3. There is 5. Can you see them? So these are monitoring something that's happening on the output of the amplifier. You can see it's kind of like connected into this circuit. Okay, those two. We also have 2 and 4 down here, which are doing the same on the other channel for both the positive and negative side of the amplifier. Number 6 is the one we looked at. This is the positive temperature coefficient on the transformer to make sure the transformer isn't overheating. And that's what we have. Yeah. So the arrow is basically pointing in the direction of the signal. Okay. I wouldn't say they're exactly right because timing 4 is down here and not up there. Yeah, and 2 is here. So that's basically it. Well, at least we have all of them. So what we need to do is identify these diodes and have a look to see if any of them are more positive on the anode than they are on the cathode. The cathode should all be the same. That 3 point something we know is on the timing signal. The only one which is slightly different is the one that monitors this supply. So here I would say the cathode should be positive because these should not be conducting down to this negative rail here somewhere. Okay, so let's have a look to see what's on these diodes. We just need to find them first. They're all 1N4148 diodes, which are the little red and black ones, so it kind of makes them a little bit easier to find than they may otherwise be. Okay guys, so I've found them all. So I put little white markers on. D19 is here. Okay, D7 and 8, which are the 2 effectively in parallel near the front. Yeah, D7, D8. Then the others are right near the back. So because the fans are in the way, these are difficult to test. But we have D120. And D320. If I remove the fans, I can get to them. And then 121 and 321 are kind of in front of the heat sinks, somewhere near here. Yeah, there's 321. I've put the marker on it now. And 121 is there. Okay, so I can get to some of these, the ones near the front. It's just the ones right at the back that are a bit of a pain to get to. In fact, these are right down by the side of the transformer. Look, those ones are right down by the side of the transformer, so it's a bit hard to get down there. The other ones are not so bad. I think, seeing as I'm here now and I have all this out, this circuitry here is part of the protect circuit, and this is right at the back of the amplifier. Now, I know when I fixed a similar one of these before, I had short circuit transistor, and I also had a burned track that was underneath a resistor. Don't know if you remember that video a long time ago. It was a burned track with a hole in it underneath the resistor. So while we're here, let's just have a look at the back, because this is not quite so easy to probe. Okay. Do I have any holes? Yeah, any burnt tracks under resistors? This is how I found the last one. I'm not sure I could find that video. That was a very long time ago. Oh, don't say anything obvious under this lot. Okay, let's look at the other side. Yeah, I don't really see anything obvious here either. But while I'm here, let's test these diodes. Let's test these transistors. If this lot looks okay, then I'll connect it all back up and see if we can measure the voltage on these diodes. Reads good. Just try to get a good connection on it. Yeah, reads good. Good. The one that I'm interested in, 120. Reads good. And then we go to the other side. Okay, so 320. Reads good. And then all the ones across the back. And then we'll try the transistors as well. Hope you agree, it just makes sense to do this while I'm here. And this is the area I had a fault on another similar powered amp mixer. Yeah, a good while ago. Okay, transistors. With a bit of luck, I can do them from this side. That doesn't read. Maybe these are PNP. We'll find out in a minute. Go the other way around. Okay. Swap the other way around. Yeah, that's a PNP. Reads okay. Next one. Is it the same? Yeah, PNP. Reads okay. Next one here. No, that's like a little resistor thing, thermistor or something. We have two here. Can we get to these? Let's see. That reads low, but it could have a base emitter resistor. That is the emitter after all. Can't even get into this one. No, I can't easily get to that one. Let's try from underneath. So that reads open. That reads open. This being the base. That reads like a junction. And this reads like a junction now, okay? I probably wasn't probing it properly before. Too much stuff in the way. Here's another one. This looks like an NPN. There's another one. Oh, and one that somebody's changed at the end. Not me. Yeah. One that somebody's already changed. So somebody's worked on this before. Clearly. NPN reads okay. This one reads short. Yeah. This might be one of those current mirror things where two pins are connected together anyway. Let's have a look. Yeah, do you see it? So base is connected to collector. Just zoom in on it. Yeah, you can see the track there. So somebody's changed this thinking this is faulty. Yeah. They were fooled by the current mirror. I'm sure you guys won't be because we've seen them before. Okay. And the other side we can see the current mirror. Yeah. Base collector connected together. That is not faulty. Okay, another one. Looks like an NPN transistor. Two more here. That's the one that has that low resistance, which is the same as the other side, which makes me think that is actually okay. Yeah, we had that on the other side. Yeah. Another one that somebody's changed. Oh, no, just a bad connection. Obviously, whoever has been changing these doesn't know about cleaning the flux off the board. Sorry guys, that is just shoddy work. There's no need for it. Would you agree with me? Cowboys, amateurs. Yeah. Let's carry on a bit. We have some bad tracks here, like corrosion. I'm going to test that track in a minute to make sure it's okay. We have two at the end, so this is probably a PNP. Reads okay. Reads okay. And this one I think is the same. Okay. Yeah, Right, so these tracks, let's have a look at that. I think they're probably okay. So from here, goes all the way across to here. Yeah, that is okay. And the other side didn't have that problem. Right, so we can pretty much say the stuff back here is okay. More shoddy workmanship, of course. So the next thing then is going to be to put this together to see how many of these diodes we can actually get to, and I want to see if I can figure out which one is triggering this protection.